Okay, so you did pendulum lab number one. All right, number one, we were testing whether the distance the pendulum swings affects how many times it swings in a minute. Okay, remember, we're doing a controlled experiment. And what that means is there's three different main variables, and we want to make sure we're only testing one variable at a time by making sure the other ones stay the same. Okay, so when you did this pendulum lab number one, controlled variables would be the length of string should remain the same in each test. Well, yeah, you set it up and it stayed the same. The mass of the bob should be another controlled variable. Yeah, well, you use the same object that you had, and so that would stay controlled. So all you're doing is testing four times through and then averaging the results of how many times it swings in a minute. Now, you probably timed it as 30 seconds and doubled it like I suggested. But what we get is the rate of swinging. How many times does it swing in 1 minute? And does it change if it's just swinging a little bit versus a medium amount versus a lot of amount? Okay. And the answer is, so it might have varied a little bit in your data, but I'm going to tell you, it doesn't really affect it. Now, I definitely, in my experience, I've seen kids that just do it a little bit. Sometimes air resistance will have more effect on that one than on this one. And that will, because it has less energy it's swinging with, so it's harder to push the air out of the way. So sometimes you'll get a less swings, like a little bit, right? A little bit. Let's say margin of error is one swing per minute, right? If you're within a swing per minute, then it had no real impact. Okay, now here's the deal. This is what confused Galileo, right? When he observed in a cathedral at Pisa that this big chandelier, when it was just rocking for a big distance and counted 100 heartbeats, it was the same number of swings in 100 heartbeats as when it was barely rocking across. And he was thinking, how could that possibly be? Because he was figuring it has to be, since it's got further to go on the bigger swings, it should take it longer. But here's the thing, it doesn't take it longer. It takes it the exact same amount to go this far, one, two, three, as it does to go this far, because it's going faster. Now, this is the kind of the key concept. And, try to your best to figure this. I'm not going to have a test question specifically on this, but it takes the same amount of time to go a greater distance as a smaller distance because it's going at a greater velocity, a greater speed is what it's called. So you say this word speed. How fast does it swing? Well, there's a difference between the rate of swinging, how many times it swings in a minute, and the speed it's moving. Because the faster it's moving, the further it can go in a given amount of time. Does that make sense? You see what I'm saying? So that's what Galileo figured out. He's like, wait a second. Okay, so this system, when it's just barely moving, it's not going as fast a velocity, the same amount of time to go less distance than when it's swinging like that. Okay? And he figured out, okay, well, what's going on here then? The big difference is the point where you release it from. Because if you figured, he also did these series of labs with ramps. It's like, okay, if you roll a ball down a ramp that doesn't have very much angle to it, it doesn't go very fast, right? But if you roll it down a really steep ramp, that's what's going on if you release it from here. Zoom! So it goes with a lot more speed, a lot more velocity, it's called, right? And so it goes a greater distance in the same amount of time. In other words, the distance it swings, or another way of thinking of it is the angle it's swinging at, which I actually like a little bit better, is it doesn't affect how long it takes to swing back and forth. It doesn't affect how many times it swings in a minute. Now, here's a little demonstration from a guy at MIT, right? Massachusetts Institute of Technology. Arguably the finest science college university in the world, or at least one of the top five. Let's just put it that way. His name is Walter Lewin. Unfortunately, he's retired and passed away. I'm sad to say. But he was recognized as the favorite professor at MIT for many years in a row. And I'm going to show you a little clip from one of his classes where he demonstrates, where he uses Galileo's formula, which you'll see on the chalkboard. And I'm not going to go over that. It's a square root kind of thing. But he uses it to predict how many times it will swing in a minute using Galileo's formula. and he shows whether it's swinging a certain distance versus another distance. How long? How in his case is how long does it take it to do 10 swings? Okay, so check this out. Okay, all right.
So let's do that first. I will move this out of the way, because if that 15-kilogram object hits this, that is not funny. All right. 0. I have a mark here on the floor. This is about 5 degrees. And this is about 10 degrees. I will first do it from 5 degrees. I will let it swing one oscillation, and when it comes to a halt here, I will start the timer. That's for me the easiest. But I count on you when it comes to counting. You ready? You ready? You sure? I'm ready too. Okay. Now keep counting, and don't confuse me again now. You're completely responsible for the counting. So all you have to tell me is when 8 or 9 is coming up. That's all I want to know. Don't even bother me with 3. Don't even bother me with 4. Just let me know when I have to get in position for the final kill. Notice there's almost no damping on this pendulum. The amplitude remains almost the same. Whereas with the air track, you could actually see that there was already some kind of friction. It was, where are we now? 9? 9, right? $45.70. 45.70. Where's my chalk? 45.70. What was my prediction? Yeah, exactly. You get the picture. That is pure luck, because my accuracy is no better than a tenth of a second. Now we do from 10 degrees. And I want to show you now that the effect on the angle, when you go from 5 to 10, is small. So small that you cannot measure it within the accuracy of your measurement. Yeah. Okay. Again, relax and count. Ah, nerve-wracking. Where are we now? 7. Did you expect anything else? 45.75.